Hello everybody, welcome to another video lesson. Today we're starting our unit on conic sections, all right? So we're going to get introduced to conic sections, and then we are going to take a specific look at parabolas, okay? So by the end of this video, we'll be able to analyze, graph, and write equations for parabolas as well as tangent lines, okay? So let's take a look at this concept of conic sections. What are conic sections? Well, they are curves that are obtained when we have an intersection between a cone and a plane, okay? And that's kind of hard to think about, so we're going to visualize it here in a second. They're also referred to as conics, okay? So if you ever hear me say conics, conics are conic sections, same thing, all right? So today we're going to look at the parabola, but in this unit we're going to look at 4 different types of conic sections, okay? The first one being a parabola. So this is the cone that we're talking about, okay? This red shape, I've got this kind of double inverted cone here, okay? Now this cone actually goes forever in both directions, okay? But we typically just look at a section of the cone to kind of help us understand conceptually what we're doing here, all right? And then here, this kind of purple rectangle here, this is the plane that I have. And hopefully you can see it's at this angle and it is intersecting and kind of slicing through these cones here, giving us this yellow highlighted shape of a parabola, okay? So you guys have seen parabolas before, but now we're going to look at parabolas in this different context of conic sections, okay? Now, if I take this plane and I start rotating it, we start to get different types of shapes, okay? One of them being if I have the plane that is parallel with the ends of this cone, we're going to get a circle, okay? We're going to get a circle like this, and a circle is just a very specific type of ellipse, okay? So if I were to rotate this plane just a little bit, but not enough to break the side of my cone, then we're going to get an ellipse like this. All right, and then finally our fourth one is going to be a hyperbola, which we get if the plane intersects both sides of this kind of double cone here. All right, so now I have what looks like 2 parabolas, which we refer to as a hyperbola, okay? And these open in opposite directions, as you can kind of see with this yellow line, okay? Or this yellow curve, rather. All right, so those are the 4 different types of conic sections we're going to look at in this unit. But before we take a look at parabolas, I just want to also touch on these degenerate conics. Okay, degenerate conics are when our plane intersects the vertex of the cone. Okay, and there are 3 specific outcomes we get here. The first one being a point. Okay, so this is the vertex of my cone. Hopefully you can see that, the vertex of my cone here, and we are intersecting that vertex at that specific point, okay? So the degenerate conic that we get is just the point, all right? And then if we go ahead and rotate that plane enough, it's going to intersect the outside of the cone, okay? And we just get this line, okay? We just get this single line when we rotate it to a specific angle, okay? The angle that is parallel with the outside of this cone, okay? And then if I keep rotating that, you may get 2 intersecting lines, okay? Hopefully you can see that with this little sketch here, or this graphic. We have 2 intersecting lines that are the intersections between the outside of the cone and the plane, all right? So those are degenerate conics. We're not going to get into them too much in this unit, but I did want you to have an introduction to them nonetheless, all right? Okay, now we can go ahead and get into parabolas, all right, and equations for parabolas. Okay, so you guys have thought of parabolas previously as these equations with a degree of 2, right? Our quadratics yield parabolas. Okay, but now we have sort of a different context for them. Okay, so we have a lot of vocabulary, so make sure you guys are writing down all this vocabulary for this whole unit. Okay. Okay, first one being a locus. Okay, a locus is a set of points that fulfill a specific property. All right, so a parabola is a locus of points. Okay, and the property that they are fulfilling is that the points on the plane. The points are equidistant from a fixed point, and a specific line, a fixed point and a specific line. And that fixed point is called our focus, okay? Our focus is the fixed point, and then the specific line is called our directrix, right? And then we also have our axis of symmetry, okay? That's the line that's perpendicular to the directrix, there should be an R in there, the directrix, through the focus, okay? You guys think of the, prior to today, I've thought of the axis of symmetry as the sort of line that our parabola is symmetrical about, which is still true, and it goes through the vertex, okay, which we have here. Okay, that's the intersection of the parabola and our axis of symmetry, okay, which we've seen that before. But it also, our axis of symmetry also goes through the directrix and the focus, okay? All right, and now let's kind of visualize these a little bit. Okay, so here I have our curve. We have our curve that is our parabola here. Okay, and then our vertex we've seen before, but now we have this focus and our directrix. Okay, so our directrix and our focus, okay, are going to be equidistant from this vertex. Okay, so keep that in mind. So this distance here is the same as this distance from the focus to the vertex, okay? These are the same distance. Okay, and actually every point on this parabola, okay, has the same distance from the focus to the directrix, okay? And it's hard to draw it to scale, but that is the definition of our parabola, okay? That distance is the same. And keep in mind, when I have a point and I take the distance from a point to any line, that's always going to be the perpendicular distance here, okay? So I wouldn't take the distance from this point to the line like this, okay? We're not going to do that. But we do take the perpendicular distance from a point to a line, kind of like I drew here, although it is a bit sloppy, all right? Okay, let's take a look at our equations and putting together these equations and how we come up with them. Okay, so I've got this sideways facing parabola here. Okay, now I've got our vertex and our focus, and then we've got our directrix here. Go ahead and label these. Okay, our directrix and our axis of symmetry. All right, and you're probably thinking, okay, we've got some formulas here. We've got some equations rather. Y equals k, x equals h minus d. Where are those coming from? Well, we're going to go ahead and assign some generic coordinates to our vertex and to this point here. Okay, this is the point that we're looking at. Okay, the point has the coordinates x, y, and the vertex always has the coordinates h, k. Okay, so then this point on our directrix has these coordinates h minus d, y, and then this point d here has the coordinates h minus d, k. Okay, and we can see that if we have an x value on our vertex of h, and I have this distance d to our capital D, okay, that's just going to be h minus d. So that's where we get this h minus d coordinate here. All right, and then our k's don't change. That's the y value, but it is a horizontal line, so the y values all stay the same. Okay, and then same with my f. I'm starting at this this x value here, right, of h, and then I'm adding d to get to the x value for f. Okay, so that's kind of, hopefully you can see how we get these coordinates for m, d, and f. All right. Okay, so now we need to take a look at the distance here between m and p, so this distance pm, and p and f, okay, this distance pf. Now, the definition of a parabola states that those are going to be equal to each other, okay, and it is hard to draw to scale, okay, but hopefully you can see that these are kind of close to the same distance here, but in fact they are always going to be the same distance, so let's go ahead and use our distance formula, okay. And I think I flipped these around here, so I've got PF equals PM here. But what we have is just our distance formula, okay? And since we have square roots on both sides, we can go ahead and get rid of those. And all that's left is what's under the square roots, okay? And then this y minus y goes to 0, okay? So that's going to go away. So I'm left with x minus h plus d, quantity squared, plus y minus k quantity squared equals x minus h minus d quantity squared. Okay, so now we have a lot of kind of expanding, a lot of room for error on this type of proof, but it is all math that we are very capable of doing. Okay, so all I'm doing in this step here is I am foiling out this x minus h plus d quantity squared, and I'm foiling out my x minus h minus d quantity squared. All right, so when I do that, I get x squared minus 2x h plus d plus h plus d quantity squared, okay, equals y minus k quantity squared. And I'm going to leave that as it is throughout this proof, and you'll see y at the end. And then we've got x squared minus 2x h minus d plus h minus d quantity squared. Okay, so I can further expand these h minus d's and h plus d quantity squared, and I can go ahead and distribute this 2x to both this x, or the h plus d and h minus d. Okay, so now I have this whole long equation here, but I can start to simplify at this point because I've got x squareds and 2xh, negative 2xh on both sides, and I've got h squared on both sides and d squared on both sides. Okay, so those start to go away. Okay, now I want to get this y minus k quantity squared all on its own, so I'm going to add 2xd and subtract 2hd. Okay, and what I get is y minus k quantity squared equals 4xd minus 4hd. And from here, I can go ahead and factor out a 4d, right? That's, again, d is this distance between the vertex and the focus and the vertex and the directrix. Okay, and I'm left with this generic formula right here for our parabola equations. Okay, so I'm going to give you on the next slide. This is our our standard form for our parabola equations. Okay, so go ahead and write this down, sketch this out, and make sure you have all the orientations, vertex, focus, axis of symmetry, and directrix for both upward and downward facing parabolas as well as sideways facing parabolas. Okay, so this would be upright and sideways facing parabolas. Okay. Okay, so a bit of a long intro, but now we know what conics are and what parabolas are, so let's get into our examples. Okay, so for this one, we're just going to identify some aspects of our parabola, and then we're going to graph it, all right? Okay, so here I see that my x squared, or my x term, is what's being squared here, right? So I've got x minus h quantity squared, so that tells me that I have this upward or downward facing parabola, okay? So now I'll go ahead and I can kind of figure out what my h and my k are. Okay, so since this should be y minus k, that tells me that k is negative 3 since I have y plus 3. Okay, and then here I've got 8, okay, which is actually equal to 4p, okay, because this coefficient right here should be 4p. Okay, but it's 8, so from that I can set 8 equal to 4p and solve for p, and I get that p is equal to 2. Okay, so I've got h, k, and p, and I can start figuring out my points that I need to graph this thing. Okay, so my vertex is always hk, so that's going to be 4, negative 3. My focus for an upright parabola is going to be hk plus p, so that's going to be 4, negative 1. And then my axis of symmetry, x equals h, so that's x equals 4. And my directrix, y equals k minus p, so that's going to be y equals negative 5. Okay, so now I'm going to take this and I'm going to solve this equation that we're given, where I'm going to solve this for y, so I can go ahead and calculate some other points. So when I do that, this is my equation for y. Okay, and I know that this is an upright parabola, so I know this point, this is my vertex, right? And I can plug in some points 0 and 2, but I also know that it's going to be symmetric about the axis of symmetry, right, which cuts through the vertex here at 4, negative 3. Okay, so if I go 2 to the left and I get negative 2.5, and then I go 4 to the left and I get 1, well, I know if I go 2 to the right I should get negative 2.5. And if I go 4 to the right, I should get negative 1. Okay, so I can easily come up with 2 additional points to graph here. And off of this table, we can go ahead and graph everything we need for this parabola. Okay, so I've got all my points, I've got the curve, I've got the focus, the axis of symmetry, and the directrix is everything that you need when graphing a parabola like this. Okay. All right, let's take a look at standard form. Okay, we're going to write the equation in standard form, identify vertex, focus, axis of symmetry, and directrix again. Okay, and then we're going to graph it. Okay, so our general form looks like this up here in the top right. Okay, this is different though than our standard form. Okay, what you'll see in your book, this is our general form for all conics where a, b, and c are not equal to 0. Okay, but our standard form is what we just looked at in the previous slides. Okay, especially for parabolas. All right, so this is general form for all conics, which we'll use later in the unit. But standard form is different. Okay, standard form is what I gave you guys on slide 6. Okay, so let's go ahead and put our equation here into standard form. So I'm going to move this 15 over, and then I'm going to factor out a 3. And then since I have 3 on both sides, I can go ahead and cancel those out. That's just a scalar. Okay, now I've got this y squared plus 2y on this side. We need to go ahead, this needs to be a perfect square, right? So we need to complete the square on the left-hand side, okay? Because I want this to be y plus or minus something squared, quantity squared, right? Because that's what we saw in standard form. So in order to complete the square, I'm going to, what's our 2-step process? I take this coefficient, I divide it by 2, and I square it, okay? So 2 over 2 is 1, okay, squared is 1. So I added 1 to this side, which means I have to add 1 to the other side of my equation as well, all right? And then when I simplify that, I get y plus 1 squared equals 4x minus 4. And then my final standard form equation is going to be, when I factor out this 4, I get y plus 1 squared equals 4x minus 1. Okay. Now I know that since the y term is what's being squared, that's going to be a sideways parabola. Okay. But if you need help with figuring out which way it opens, you can actually take a look at this 4p term right here. Okay. This is positive, which means it is going to open to the right. Okay. When this term is positive, it either opens to the right or up. Okay. If it's an upright parabola, then it's going to open up. Okay. If this is negative, then it's either going to open to the left or down. Okay. Left or down if it's negative, right or up if it's positive. Okay. So just keep that in mind when you're trying to figure out the orientation of your parabola. Okay. So now we can go ahead and find our vertex, focus, axis of symmetry, and directrix. I keep forgetting to put an R in directrix. Okay, but directrix, there we go. Okay, I know my HK and I can figure out my P value, okay, because this is 4, but it really is representing 4P. So I know that P is just 1. Okay, so then I can find my vertex, focus, axis of symmetry, and directrix. All right. Now we can go ahead and create our table again. When we do that, when I solve for y here, I get this plus or minus term, which makes sense because when I input an x value, I should get 2 y outputs, okay? Should get 2 y outputs because this is a sideways parabola, okay? So if I plug in 1, I should get negative 1 because that is my vertex, okay, so that checks out. If I plug in 2, see now I get positive 2 minus 1, that gives me 1. But I also could have negative 2 minus 1, which gives me negative 3. Okay, so that's important to have this plus or minus in there because that's going to give us our 2 outputs. And the same if I input 5 into this equation here, then I would get 3 and negative 5. All right. So when we go to graph this, let's see, I've got all my points, my focus, my axis of symmetry, my directrix here, and then I can go ahead and draw in my curve. Okay. Okay, just 2 more examples here. We'll try to get through them quickly. Okay, let's see. We're going to write an equation and then graph a parabola with the given characteristics. Okay, so we're given a bunch of characteristics here. We're given the focus and the vertex. Okay, so we need to kind of figure out our orientation first of all. Okay, so our orientation if I just kind of graph out these 2 points here, okay, I've got the same x value on these 2 points between my focus and my vertex, which means that it's going to be an upright facing parabola, okay, or, well, yeah, it's going to be upright facing parabola because my focus is always kind of inside my curve, right? Okay, so since my focus is above my vertex, I know it's going to be upright facing. Okay, okay, so from here, this p value, this is just the distance here between the focus and the vertex, right? This is my p value. Okay, so I go down 1, 2, 3 to get to my vertex. I go up 1, 2, 3 to get from vertex to focus. Okay, so my p value is 3. Okay. Okay, so this is my general form equation for my upright. Sorry, this is my standard form equation for an upright parabola. Okay, so I've got vertex. That's going to be hk. So I can figure out what h is and what k is. Okay, and then I can go ahead and substitute those into my equation. Okay, so I've got x plus 6 squared equals 12y plus 1. Okay, and again, I got this 12 because this is 4p, right? 4p, and I said that p was 3, so 4 times 3 is going to be 12, okay? Okay, so that is the standard form equation here. So you guys go ahead and pause the video and then find the standard form equation given this information here, okay? Go ahead and pause the video, see if you can't find that out on your own. Okay, so this is our standard form equation. Let's see, we've got it right here, and this is the process that I used to find that information, okay? So go ahead and check your work there. And we'll keep moving to the graphing section. Okay, so we have our equation here. We're going to go ahead and graph this, all right? Okay, so I've got my focus and my vertex. We found that out first, and from that we can also tell our axis of symmetry, okay? And then once we know our p-value, we can easily find our directrix. Okay, and then we got our points, so we can go ahead and plot our points and draw our graph, okay, or draw our curve, right? Okay, so same thing on the right-hand side. Hopefully you guys can pause this and sketch it yourself. Okay, but again, we have our vertex, our focus, we have our distance of p in between the two. Distance of p in between the two. Once we have that p distance, we can find our directrix, and then we can go ahead and plot some points. We know it's which way it opens, okay, and it contains our points 8, -7, and so yeah, we're good to go. Okay, last example here. Write an equation for the line tangent to the parabola at the given point, okay? So going over tangent lines real quick, again, those are lines that intersect a curve at just one point, okay, at just one point. So if this is my curve, if this is my parabola in blue here, okay, this is in red, my tangent line, okay, this one point that it intersects is going to be the point of tangency, okay? Point of tangency is how we refer to that, all right? Okay, now understand that with this tangent line, okay, when I have a tangent line with this parabola, I've got a point here, and it is going to form this triangle. And we're going to use this information to help us make our tangent line, okay, our equation for tangent line. Okay, because this triangle has two legs that are the same distance, all right? So we've got a point here, that's our point of tangency. The distance from that point to the focus is the same distance as it is from the focus to where our tangent line intersects with our axis of symmetry, okay? So you've got this 3 points creating this triangle, and two legs on this triangle have the same distance, okay? So just keep that in mind. Okay, so we're going to go ahead and write our equation for our parabola in standard form here. Okay, so I'm just multiplying each term by 4. And then let's see, I am getting the y term on its own, and then I'll go ahead and factor out my -4 here. Okay, so I've got y minus 0 squared equals -4 quantity x minus 5, okay? Now, I've got, again, a negative 4 here, okay? And I know that it is going to be a sideways facing parabola because my y term is squared. Okay, so I know it's sideways facing. Since this is negative, I know it's going to open to the left, okay? So I can kind of figure out my orientation there. All right, so from our equation, we can go ahead and figure out our hk and our p values, okay, which we've done before. Okay, our vertex and our focus have these specific values, okay, based on those hk and p. So it's going to be 5, 0, and 4, 0. Our directrix is going to be x equals 6. Okay, so now we can go ahead and start graphing, okay? Okay, so we've got our 3 points here, all right? We've got our parabola. We've got our point of tangency. That's actually given. Okay, that's here. Okay. So that's that's 1, negative 4, okay? So that distance there, well, let's go ahead and just draw out our tangent line, okay? Because you see this second point here. Probably wondering what that is. Okay, so I've got point 1, point 2, and our focus. And you can kind of see here how we have this triangle that's formed, and our 2 legs in blue are what are going to be equidistant, okay? So it's the same distance from P1 to F and P2 to F, okay? So we're going to go ahead and we're going to use our distance formula. So in order to do that, I need to have an x1, y1, and an x2, y2. Okay, so I'm going to use the first point, our point of tangency, along with our focus coordinates, okay, for x1, y1, and x2, y2. And using our distance formula, I'll just go ahead and plug those in, solve that for our distance, and we have a distance of 5, okay? And I know this is great because I know if the distance from F to P1 is 5, then the distance from F to P2 is also 5, right? Okay, so I can really just count over from this 4, 0. Okay, I can count over 1, 2, 3, 4, 5. Boom, okay? Now this was a sketch, okay, so you can see that it's close though, right? Okay, it's very close, 1, 2, 3, 4, 5, so that's actually where that second point is. Okay, but the illustration still works just for reference for us. Okay, so our second point is going to be 9, 0, okay? So we need that point because why? Well, in order to have the equation for a line, we need at least 1 point, and we need the slope, right? And in this case, we don't have the slope, but we can find the slope with these 2 lines, right? So from P1 to P2, we can go ahead and use our slope formula, and we see that we have a slope of positive 1/2, okay? So now I can go ahead and use point slope form since I have 1 point and the slope, and I can go ahead and plug in. Doesn't matter which point I plug in, but I'm going to use 9, 0. Okay, so I've got y minus 0 equals 1/2 x minus 9, and then I can go ahead and solve for y, and I get the equation for the tangent line on this parabola, okay, at the given point. All right, so that is all we have for today, guys. Sorry for such a long video, but yeah, we are underway with conic sections, and good luck with your practice.